So I have a confession after this very nice intro video. This is my first time at RFIC. It's also my first time at IMS. In fact, there's probably only one reason for me to be standing here, and that's because of a very, very large team of very talented people at IMEC that have provided me with lots of insights about where we want to go. And it's a huge team, but just so you know, there's always room for more if you think about joining a very exciting team. That being said, I was thinking about the future, and the future is a fickle thing. And this image triggered me. I don't know if anybody knows what this image is. It's in Portugal. It's a cork harvesting enterprise, in fact. And this is a new material. You may not know about this, but when you think about materials for the next generation, cork may actually be important. Because you can make very nice antennas that could go into cork floors that then radiate your Wi-Fi signals up from the floor, having perfect coverage. By the way, the design is for a full 5 gigahertz band with 300 megahertz spare on each side, so 1.3 gigahertz of bandwidth. So it's not that far-fetched. Now, I don't want to talk about cork today. I want to talk about other stuff as well. So what about networks of the future and the materials of the past? And I think it's going to be a perfect complement to what Greg just talked about, because I'm not going to talk about digital at all. Do the networks actually care? And to understand that, we first have to understand what do the networks of the future actually look like. The networks of the future are becoming suspiciously, even so, homogeneous. If you look at the network, what is a network today consists of is essentially one, you have interchip, then you have intra-board and inter-board, which then goes into a rack in a data center. The rack in a data center connects to some, well, local other data centers, maybe a long-haul connection. That long-haul connection and the data centers are connected in a metro ring with some central offices, because of course operators don't want to call it data centers, they call it central offices. Where they connect their access equipment, passive optical networks, their 5G backhaul and midhaul, and then all the way at the end, you finally reach the radio access network and the device you may be holding in your hand or that's sitting on your desk. Interestingly, if you look at the typical bandwidths that are necessary, not bandwidths in gigahertz, but throughput, you see that the bandwidths are all reaching sort of the same general amount of bandwidth necessary. It's about half a terabyte to a terabyte. In some cases, it's less, but you need multiple links or you have some multiplexing. In other cases, and there's a few exceptions there, for example, passive optical systems going to the home, not quite that high bandwidth yet, and there's a few things at the end of the 5G systems that also don't actually reach the full half terabyte yet. But on the whole, half a terabyte to a terabyte is what you need in a network, and it's actually driven all the way by the thing in the top corner, by the radio access network, because that's where you have thousands and maybe millions in the future of users and devices that all need some bandwidth, and all of that bandwidth has to go all the way back to the data center. So if you look at the needs that have been driving this, well, wireless networks essentially have three trade-offs. They have capacity as a trade-off, reliability as a trade-off, and latency as a trade-off. And you can, of course, pick only two. You can't have all three. And industry, and that's why everything is converging to the same amount of bandwidth everywhere, has been extremely efficient at that top left-hand corner, capacity. And why? Well, mainly because of Game of Thrones. Well, mainly because we want to transmit ever more data, specifically to people that want to pay for entertainment. Which means that in general, the wireless evolution in broadband has been ridiculously boring. And if you look at it, and frankly, it's not only LTE and LTE Advanced, let's not forget there's other technologies like Wi-Fi out there as well. But frankly, if you look at the evolution, it's, well, 11N LTE, then you had AC and LTE Advanced, then you had AD and LTE Advanced Professional. Don't ask me who comes up with the names. And essentially, all of those have gone into the same direction. They've gone to ever wider bandwidths, more and more bands, more and more carrier aggregation, or channels if you want to talk about Wi-Fi. They're using MIMO, and frankly, if you draw the line even further to AX and AY or 5G, they're all pretty much the same. And we've solved the problem, although there's a lot of digital involved, as Greg has said, and there's been some very nice outcomes there. There's possibilities to do 60 gigahertz in CMOS. To get all of that stuff into the digital, you need high-speed ADCs, and you can even do high-speed ADCs in 16 nanometer FinFET, up to 3.2 gigasamples per second for all of that digital processing that is required. So we know more or less where that has gone. So where are we going after all of this boring stuff? Well, to know where we're going, we first have to know why are we there? And we're there because people hate boundaries. And in the past, we had boundaries on face-to-face communications. So we invented the post office. Well, you could communicate with anybody, but you still had to go to a certain place. Then we invented the phone that was in your house. You could talk anytime, but only at your house. And now we have mobile phones, and you can talk anywhere, any place. Same thing happened for entertainment. Entertainment, in the past, you needed to wait for the BART or the circus to come to town, and you had entertainment. And then we had movie theaters, then you had TV in the house, and now you can play on your whatever Wi-Fi power PlayStation thing in the back of the car while your parents are driving, and you don't have to have any interaction with your parents anymore. Right? So where are we going after that? Well, where are we going after that is we've become incredibly good at building systems that connect to what are essentially huge filing cabinets. You have an end device that goes all the way back to a huge filing cabinet. But that's not going to continue working. I mean, if you look at the amount of processing that's required for the new applications, take autonomous cars, take in automation, take digital twins, you see very quickly that the amount of power is in the order of several tens to 100 watts to do CNN type, so neural network, machine learning type applications. So you're, if you can see it, somewhere on the right-hand side. And you could say, well, I don't need this in my phone, I don't need this on my end device, because I can just transmit stuff to the cloud. Problem is, if you look at those very nice LiDARs, radars, and so on, and you look at the amount of data, and you take a very optimistic amount of femtojoules per bit, you end up in exactly the same space. So you need edge computing, but even edge computing isn't sufficient, because edge computing would also still consume too much power. So we need something better. And it's that something better that is pushing the challenge in everything outside of traditional broadband. So what are the challenges there? Where do we see the future outside of traditional broadband? Well, the first one is there's not going to be a phone. I mean, the interface of the future is something three-dimensional. It's mixed reality. It's not virtual reality. It's mixed reality where you have artificial images interacting with the real world. Magic Leap is a very first small step, but you want to go beyond that. This could be also the interface. Maybe there's no glasses involved even, but the amount of bandwidth for the light field displays is typically of the order 100, 200, 300 gigabits per second, even taking into account compression. So you need something better. The cars, autonomous cars, great, but they cannot transmit everything. Maybe they want to talk to each other. There's no human involved. Why should they be limited to the 20 or 100 megabits per second, which is our human interface bandwidth? They can transmit at a much higher rate. Maybe they just want to tell you or tell the other car what it has learned. Not only cars, also machines in factories. Maybe factories want to talk to each other. Or perhaps, I mean, since we're in Boston anyway, maybe autonomous robots want to tell each other what they learned, what they saw, without having to go through a central data center, which from a privacy perspective would also be better. All of those things mean there are good reasons for much higher bandwidth and much higher speeds of wireless communications, going from intra-device communications, digital light processing, light field displays, multi-user AR, VR, all the way to the more traditional fixed wireless access, because frankly, digging up the roads and putting in fiber everywhere won't necessarily work everywhere. So how do we solve this? Well, the first thing is, there is actually room for it. And as you know, in the US, the FCC has recently highlighted the fact that they will be more forthcoming in licenses between 95 gigahertz up to 3 terahertz. My slide wasn't wide enough to actually go up to 3 terahertz, but you get the idea. There's lots of space there. The question is how to address that space. Frankly, it's not only for communications, just to be clear, but Greg already highlighted that. There's other things you can do as well. You can do terahertz imaging if you can integrate on a silicon photonics platform. You can do spectroscopy of living cells, for example. This is an example of the group of Dominique at the KU Leuven and Bart Nauwelaerts are actually doing digitally interleaved capacitors to actually get a full spectrum from 300 kilohertz to 50 gigahertz to detect which kinds of cells are growing and how they are growing. So there's a lot more things that you can do than just communications. All of that requires, of course, to handle those higher speed signals. So how do you handle higher speed signals? How do you get to those millimeter waves and how you transmit them? Now that's an onion. So let's peel the onion. And the outer layer of the onion is the enclosure. And even in the enclosure, you already have to be careful because every decibel matters. And in fact, if you look at the traditional enclosure, which is epoxy fiberglass, or you look at the best possible enclosure, which is a kind of ultra-high density polyethylene, there's already a 1 dB delta at 70 gigahertz. So if you take the two sides, you already lose 2 dB if you make the wrong material choice. That's the first thing you have to remember. Materials act differently. You can't just assume they're completely passive or aren't going to attenuate at those high frequencies. So you may want to say, well, we just get rid of the enclosure. We print the antenna directly on glass and be done with it. And this is a 28 gigahertz antenna on glass. And meanwhile, a lot of people are thinking about it. But as you probably know, a lot of the new higher performance glasses are in fact completely not transparent to millimeter wave. So that's not necessarily the best solution. And secondly, you still need to get the signal to the antenna through the feeds. Now, there's two ways to get the signal to the antenna through the feeds. Well, you can use metal, but at the higher frequencies, in fact, the metal becomes the highest loss. So what do you do? Well, you can use substrate integrated waveguides. And this is an example of a 24 gigahertz antenna, in fact. And what you see is you have, here we go. You have two 3x3 arrays, and each of them is actually fed by only a single substrate integrated waveguide. And here the different antenna elements are in fact coupled inductively, so you get a perfect transmission pattern. You can go beyond that, in fact. You can actually get rid of even the substrate that's in between it and use a full air gap in the middle. And then you can drive it optoelectronically and get rid of that air gap and actually get very high efficiencies up to 90% at 60 gigahertz. And people have taken that even further. That's some example of the group at Chalmers that has even done full distributed air gap 16 by 16 arrays. Or air isn't even good enough because the air still has metal around it. Maybe you want to get rid of the metal all together, because frankly, at very high frequencies, this is a D-band 170 gigahertz example, the actual metal and the surface roughness of the metal can make a 1 to 2 dB difference. And so what we've done is some experiments, in fact, where you take a liquid crystal polymer waveguide and you actually inject the signal onto the liquid crystal polymer waveguide, which has very, very low loss. And the nice thing, it's flexible as well. So if you want to embed your communications or your radar in your car bumper, you have a double bingo. Interestingly, I mean, the solutions to that problem were already known in the 60s by Ye and Marcatelli at Bell Labs. So, you know, everything's a remix. And then finally, of course, if you really want to get rid of the feed lines, you may just want to put your antenna directly on the chip. And this is, in fact, the radiation pattern of the 140 gigahertz radar that we developed that uses, sorry about that, that in fact embeds the dipoles in the aluminum passivation layer and gets very, very nice directional directivity at 140 gigahertz, assuming you have something that can actually generate 140 gigahertz. And then beyond that, and I'm not going to go into detail there, but beyond that, there's of course still the filters, circulators, isolators that need new materials as well. One interesting filter that I actually wanted to just show you because it's an interesting approach by MIT and Purdue is in fact using FinFETs to have a joint coupled acoustic electric signal which actually achieves a Q factor of almost 50,000 at 32 gigahertz. So that's actually a rather interesting approach because it combines the FinFET together with the need for filtering in fact. But this is RFIC, and you may say that's all very nice, but these are all passive materials. What do we care, right? Can you show us how do we actually generate these signals? Well, if you want to generate the signals, the problem is that RF has taken a little bit of a secondary role to logic and high-speed digital in the past years. And you saw from analog devices, they're trying to get it back there as well. So we have to fight that, right? And this is, in fact, a roadmap that I fished up. And you can actually tell that's from 2008 because of the use of the Arial font and the very strange gradient. But even in 2008, we were already talking about FinFETs. And then beyond FinFETs, you can see there's actually 3.5 materials and other stuff. This was expected to come after 16 nanometer. Of course, today we know a little bit better. We also have fancier roadmap slides. And you see that the 3.5 channel, it's not a 3.5 device anymore, it's only a 3.5 channel has more or less shifted along, and the FinFET seems to be continuing to be the most important device. That's great, but we don't care in RF because, frankly, the cutoff of CMOS devices for RF, especially for those high frequencies, is actually becoming worse as we go to smaller technology nodes. And 16 nanometer FinFET and 70 for sure is not going to help you there. Which means, of course, that if you look at the power added efficiencies of silicon PAs, and if I upload the slides, there's all of the data points are in the backup. You actually see that as the frequency goes up, the power added efficiency keeps dropping and dropping and dropping, unfortunately. Now, first message about the materials of the past, don't write off CMOS yet, right? I mean, I showed you the radiation pattern of the 140 gigahertz radar. There's a circuit that goes with it, which is essentially a 28 nanometer CMOS, 140 gigahertz PA and receiver that actually achieves 11 dBms at a very high efficiency. So it's not impossible, it's just getting harder. Now, if you want to go above 200 or 300, I wouldn't recommend it because I don't think there's going to be improvement from 28 going down to 16, for example, but at least at 140 in the entire D-band, it's very likely that CMOS is still good enough. Now, those are all the devices there. So what you see here at the bottom is essentially FT versus Fmax for traditional planar CMOS and some FinFET devices. And of course, if you want to do better, well, you have to go to some other materials. First tries were with gallium nitride. There's been some very nice experiments with silicium germanium by CMOS. But of course, the big champions there for the very high frequencies are all the high electromobility transistors in indium phosphide and other 3.5 materials. The nice thing about that is, and remember, those are very high speed, but they're not very short gate devices. So the gate length is much relaxed, which actually also helps if you want to fabricate those things, because you don't have the same trade-off as in CMOS. The nice thing, of course, that it's more relaxed, it also has much better power handling capabilities. And so we expect that, especially once you go above 100 gigahertz, gallium arsenide and gallium nitride will become the technologies of choice. Talking about BiCMOS, we recently did a tape out of a D-band, so 140 gigahertz power amplifier with a 17 dBm peak power with 13% power added efficiency. So I think that's a record. This was in a framework of a European project called Taranto. We'll be publishing it shortly. But needless to say, the measurement essentially corroborated the design specs of a 17 dBm PSAT. So even there, after you exhausted CMOS, BiCMOS probably has quite some legs to run on. Now, once you go beyond it and you want to look inside your phone, there's an additional problem that shows up. Up till now, the millimeter wave choice in handsets has been mostly traditional CMOS, some discretes. But if you look at a 5G handset, which is expected to have a 40 dBm ERP, and you look at the spec for the amplifier, you quickly realize, and it's actually very weak on this projector, but the target area you want to be in is here. And you see that the only materials that actually remain that can have sufficiently high power added efficiency will be gallium arsenide and gallium nitride. On top of it, and the nice thing is, of course, I don't have to repeat this because my previous speaker has already said so, the entire design for 5G is not getting any easier, right? You expect you require very high levels of integration, preferably something that can go directly to an ADC in 7 nanometer CMOS and get everything shipped off to a digital processing chain. So how do you do this? Well, we've been looking at essentially monolithically integrating or sequentially integrating 3.5 on CMOS, coming back to the question that was asked earlier. And so for the sequential 3D, the main challenge, of course, is the last step. Your temperature has to be sufficiently low to allow it. The one that I like a lot, in fact, is a monolithic integration onto existing CMOS. And you know probably the saying that any sufficiently advanced technology is almost indistinguishable from magic. Well, the first time I saw these things, I was pretty sure that was magic. I mean, that was just impossible. Remember, I'm coming from a completely different background. This I think, is absolutely amazing. Essentially, it uses aspect ratio trapping of the defects, and then you can grow almost, well, close to perfect, not perfect as in photonic perfect, but good enough, 3.5 on top of it. What's also really magic is that the building of IMEC, that was built before this was actually developed, suspiciously looks like it. So, I mean, somebody was really a futurist. So what have we done? Well, essentially, we have done 2 tracks. We have a gallium arsenide-based track using those essentially nanoridges. Think of it as 3.5 FinFETs. That we actually are showing and developing on a 300 millimeter platform, which means this is compatible with a 300 millimeter high volume CMOS platform. This is mostly for what Greg also mentioned, the high integration needs for massive MIMO arrays, sub 6 gigahertz, but requiring very high power added efficiencies. And then we are looking also at the gallium nitride devices beyond base station, also for the handset, leveraging, in fact, we already have a gallium nitride on silicon platform, but that's just a silicon wafer. That's actually a power electronics, but we're taking that beyond power electronics to CMOS as well. So there's a number of challenges, growth being the obvious one. The gate stack, I think we have most of it figured out. The parasitics have been a headache. Frankly, the bigger problems right now are the low resistive contacts and actually getting away from gold and going to copper-based back end of line to actually have decent RF type devices. But we think we're pretty close to actually getting to a single stage power amplifier. So for me, this is going to be the next big flag on a 300 nanometer platform with gallium arsenide nanoridges. So where are we at? Well, this is more or less the landscape that we had. We had CMOS that was pretty okay in terms of speed, but not RF speed, huge integration, but not much of power. Where we would like to go, and that we're building today, is essentially making sure that we get these islands of monolithically integrated, either gallium nitride or gallium arsenide, and maybe beyond that indium phosphide, that you can actually build high density logic plus RF plus ADCs on the same platform, which means that from a material perspective, you can have your FinFETs or your gate all around type 3.5s for your logic. If you need more speed, You can go to BiCMOS, which actually has some results even to 1 terahertz, so it has quite some legs. It has slightly better power handling capabilities. Typically, it's 1 generation behind CMOS, so that's not too bad in terms of scaling. It's compatible with FD-SOI, so it's an added plus. Actually, I didn't put RF-SOI, which should be somewhere around here, and actually is also an interesting candidate. But then, of course, the big winners in our perspective for the materials, which are actually from the past because they're photonic materials, but for the future RF will be gallium nitride and gallium arsenide. There's a few other materials I just wanted to shortly highlight. One, it's going to generate a lot of power still. You will need to cool that, so you may want to look into yet other materials, like for example, PMMA or 3D printed liquid cooling that you can put on top of your chip. There's pump power here, which means something completely different than the power earlier. But essentially, we've shown that we can evacuate up to 50 watts from an 8x8 die using that with very nice results. And of course, beyond this, there's even other materials like graphene and so on. I think you've seen from the way I've tried to present everything, we're really looking at things that are for networks of the future, but where we actually see a path to commercialization today. Graphene is nice, but we're still far away from the same areas or the same approaches. The one promising data point on graphene, in my opinion, is the fact that although up to now people have mostly looking at graphene by exfoliation, so you grow your graphene and then you deposit tiny little flecks, which is not really reproducible, to a way where you actually grow the graphene by CVD, and then you can actually do transfer printing onto large wafers. And in fact, this transfer printing is being developed also for 3.5 on top of silicon photonics, 3.5 on top of CMOS. So it's likely that there may be some recombinant innovation there as well, which could accelerate this. So something to keep an eye out for, but compared to the other technologies I've highlighted, I think from a TRL or maturity level, it's a little bit further out. So we're at 5G. We have a lot of solutions for 5G. We have solutions for the upcoming next generations of 5G. For sure, there's already people thinking about 6G. I mean, for sure, there's people thinking about 6G. But I mean, only half kidding. There are already a lot of thoughts about what 6G would look like. That could be something like fully smart walls with metamaterials that can do beam steering. The one thing I would like to finish on is I like these system studies because they're exciting. And they call it even software-defined wallpaper and so on, RF wallpaper, millimeter wave wallpaper. But at the end of the day, you're going to need a circuit that's going to drive those things. And so while any sufficiently advanced technology is indistinguishable from magic, I would like to end to also know that any sufficiently advanced marketing is indistinguishable from technology. And this is why I come to RFIC, because frankly, you're the guys that tell me which is marketing and which is actually real. So thank you, and have a great show.